Hello everyone, my name is Eliza Yusuf, and my topic is all about decrease key and delete node operations on a Fibonacci heap. A Fibonacci heap is a tree-based data structure which consists a collection of trees with min heap or max heap property. Its operations are more efficient in terms of time complexity than those of its similar data structures like binomial heap and binary heap. We have here the two important operations. Number 1, decrease a key. It decreases the value of a key to any lower value. Number 2, delete a node. It deletes the given node. Decreasing a key. In decreasing a key operation, the value of a key is decreased to a lower value. Decreased key. Number 1, select the node to be decreased x and change its value to the new value k. Number 2, if the parent of x and y is not null, and the key of parent is greater than that of the k, then call cut x and cascading cut y subsequently. So, pag sinabi natin cut x, node x is cut or removed from its parent. So, pag sinabi naman natin cascading cut y, a cascading cut operation is recursively applied to y, potentially cutting y from its parent as well, and so up on the tree. So this ensures the heap property is maintained. Number 3, we have the update minimum. If the key of the updated node x is now smaller than the key of the current minimum node, then x becomes the new minimum node. That's all.
Hello everyone, I'll be continuing the discussion of the decrease key, which is the cut and cascading cut. So when we say cut, it is where we remove the given value or the nodes from the current position and add it to the root list. So here is the example of the cut part. So here, 26 ang i-mark yung ika-cut natin. So since the 26 is marked, already the flow goes to cut and cascading cut. So dito, tanggalin na lang natin yung 26. Natanggal na siya as the child node of the 7. Then we will gonna add it as a root node right beside the 7. And mamarkahan natin ito as a false. So here's the cascading cut. Same din sila sa process ng cut. So here, 24 naman ang cascading cut natin din. Same process. Then as the cut, if namarkahan na yung 24, puputulin na lang natin siya sa 7 at ililipat din sa root node. Then ayusin natin yung main. So since 5 is lesser than 7, then imamark natin yung 5 as a mean.
Hi, I'm Ali Arat. So I'm the one who explained the decrease key example. So this is example of decrease key, decrease 46 to 15 example. The image present as a tree structure. So our main heap is the 7 kasi siya yung pinakamaliit na value. Then itong 7, 18, 38, tinatawag natin itong root list kasi sila yung humahawak sa parents, which is the 24, 17, 23, 21, 39, 41. And it has a children, the 26, 46, 30, 52, and 35. So dito sa pic, makikita natin paano i-decrease si 46 to 15. So pinaliit natin yung value ni 46 to 15. Then we mark it red. So, mapupunta na tayo sa cutting part. Since si 24 is not null, then si 15 is parents na. Dahil naging mababa na ang value nito, i-add natin ito sa root list dahil mababa na ang kanyang value. Then, ina-mark natin si 24. So, next example naman is decreasing the number 35 to 5. So, same sa procedure doon. Yung 35, babaan natin siya ng value into 5. Then, yung 5, imamark natin siya ng red. Then, dahil naging 5 na ang value ng 35, naging maliit na to siya, i-add natin siya sa root list. Since the 26 is not null, then the 5 is parent, then i-cut natin and add ito sa root list.
Good morning, everyone, especially to you, ma'am. My name is Margaret Yarigan, and my topic for today is all about decrease key and delete node operation on a Fibonacci heap. So what I'm tackling about here today is just an example, which is decreasing 35 to 5. This is a decrease key example, actually. So the first step is decrease the value 35 to 5. So in the image, this is the image that shows a binary min-heap data structure before and after decreasing yung value node ng 35 to 5. First, let us know the initial state muna. In the initial state, both left and right in the image, bago pa ito i-decrease yung node, ang root node natin is si number 7. Here, you can see that. Kasi ito yung pinakamababang minimum value. Well, the heap property is actually well maintained. Kaya every value ng node is less than or equal doon sa value ng kanilang children. Now, here, we are going to decrease the node value of 35 and 5. However, this actually violates the min-heap property. Kayong, excuse me, kayong 5 is smaller than 26. You can see that in here, 5 is smaller than 26. Since sa taas ng 5 and 35 natin are both 26, and kapag isolve natin sila, it actually violates the min-heap property. So, what are we going to do with this? We'll find that out by proceeding into the next step. So the next step is the cut part. Since 26 is nil and 5 is lesser than its parents, cut it and add it to the root list. So this part, so basically we cut something and add it to the root list. And this will be number 5. So likely in algorithm, it involves finding yung minimum value. And with the structure presented, the algorithm search for the minimum value of 5. So instead na yung minimum value ay 7, naging 5 na. So what are we going to do is to cut yung 5, then ilagay siya sa root list. You can see in the picture na nasa root list na yung 5 instead sa baba ng 26. We're adding 5 sa root list because yung pagka-identified ng algorithm is si 5 ang mean, which is hindi naman kundi si 7. So the process of cutting and adding some node is just part of the larger algorithm para ma-rebalance yung structure ng tree. Now we move on to the step 3, which is cascading cut part. Since 26 is marked, the flow goes to cut and cascading cut. Cut 26 and add it to the root list and mark it as false. So sa image, it shows tree-like structures, and in the instruction, it said we cut the 26 and hindi pa siya sa root list. By cutting 26, this means we're removing the node containing the value 26, and this node is the child of the 7. Removing it leaves node 7 with 24. Now, why are we cascading cut it? Well, cascading cut is a process kung saan we're moving the node in order for the tree to be balanced and well structured. The reason why we're cascading cut it because dapat less than or equal yung node natin kaya yung min-heap data structure natin dahil yun yung structured min-heap data structure. Kaya ganito. 7 is less than 26, right? You can see that in here. 7 is, wait a minute. So that 7 is less than 26, which is okay na yung structure. But si 26 ay hindi naman less than tayo 24. 26 is greater than 24, kaya gimove natin siya sa root list. And this is the process called cascading cut. Next is cascading cut 24. Since the 24 is also marked again, full cut 24 and cascading cut 7, this operation result in the tree below. Diba na cascading cut or na-move natin yung 26 into the root list and ang natira na lang is si 24. See that in here? So 24 na lang natira. Bali, ang gawin natin dito is the same thing kay 26 where i-move natin siya sa root list. Now, you might be wondering, like, less than 7 naman si 24, right? But, is the structure well-balanced kapag natin is cascading cut sa 24? Diba hindi? Bali, i-move natin si 24 sa root list para maging balance lang yung ating min-heap data structure. And last step is, since 5 is lesser than 7, mark 5 as min. Since si 5 na yung lesser than kay 7, therefore siya na yung magiging min natin. And removing mga child node to 7 is actually a great idea because in the first place, hindi naman pala well-balanced yung ating tree structure. Ay bukod sa may mas lesser than pala kay 7 sa root list, yung mga child node nito, hindi pala sinusunod yung pagka-lesser than yung number. Like si 26 ay hindi pala lesser than kay 24, kaya remove natin siya. Tapos leaving 24 as a child node of 7 would also violate sa structure ng ating tree, kaya remove din natin ito. And since well-balanced na yung ating tree structure, so ang ginawa natin is i-file na yung ating min instead na si 7. So that's all. Thank you for watching. Good morning, everyone, especially to you, ma'am. My name is Margaret Hadigan, and my topic today is all about the complexity of decrease data. Wait a minute. Decrease key and delete node operation on a Fibonacci heap. So first is we have decrease key. So this operation reduce yung value ng ating key o yung mga value ng each node natin sa main heap. Ang time complexity nito is 1, where yung n ay number of element ng heap. Kasi after natin na-decrease yung heap natin, need pa natin ito siya i-bubble up or heapified up para ma-maintain yung correct position ng ating main heap property. Ano ba position nito? Well, this position kung saan yung parent node or root node ay dapat lesser than sa mga child node. Yung bubble up process takes mga logarithmic time in the worst case. Next is the late node. So this operation remove a node sa main heap. Time complexity is O log n. So when we delete a node, it involves replacing the last element ng heap. And this is called heapifying or reorganizing para ma-restore yung ating main heap property. This heapification process also takes logarithmic time in the worst case. So let us know yung mga meaning or purpose ng symbols. First is the big O notation. So the O notation is describe yung growth rate ng runtime ng ating algorithm as yung input size or n natin ay nag-i-increase. So in decrease key, we have the O1 where it means constant time. This runtime ay independent sa mga input size. Then yung delete node natin naman ay O log n where it is logarithmic time. The runtime increase logarithmically with the input size. Baka nalito kayo kung anong runtime or logarithmically time. So ang runtime kasi, this grows kapag tumataas yung ating input size. Now in logarithmically time naman yung O log n, nag-i-increase slowly yung ating runtime. Depende naman sa pag-grow size ng ating input. Now think of something like this, kapag i-double mo yung size ng iyong input, the runtime increase in a small amount lang. Now, you might be wondering what is the purpose of this table. This table only indicates the efficient operation pagdating sa pag-scaling logarithmically sa mga size ng mga heap. So that's all. Thank you.